Time travel is not real. Every sensible person knows that. You hear the phrase time travel, and you picture some crackpot in a leather jacket climbing into a machine with blinking lights, spinning a dial, and vanishing into the Middle Ages. It belongs in movies, it belongs in stories for children. It certainly does not belong in physics, and I want to tell you, as someone who has spent his life doing physics, that I believe something very close to that for a little while too. Time is time, a second is a second, your clock and my clock, if they're good clocks, they agree. That's just how the universe works. That is completely wrong. And I can prove it, not with theory alone, not with some fancy equation on a blackboard that you have to take my faith for. I can prove it with clocks, real clocks. Clocks that were put on airplanes and flown around the world. Clocks that came back showing different times. Actual measured, verified time travel performed by the United States Naval Observatory, published in Science magazine, and ignored by almost everybody who still thinks time travel is just for the movies. Let me take you through it properly, because this matters more than almost anything else in physics. It matters because it's not about what's theoretically possible somewhere far away in the distant future. It's about what is already happening, right now to you while you sit there. Start with what you think you know. You've got a wristwatch. I've got a wristwatch. We synchronize them at noon. You go for a walk, you come back, we compare, they match. We've all experienced this. Time seems to move at one rate, steady, unshakable. A second for me is a second for you. That idea is so deeply baked into the way we experience reality that questioning it feels almost insane. And yet the questioning didn't start with some lunatic. It started with one of the most careful thinkers who ever lived. Albert Einstein, sitting in a patent office in Bern, thinking about what happens when you chase a beam of light. See, Einstein asked a question nobody else had the guts to ask. He said, what if the speed of light is the same for everyone? Not just for the person standing still, but also for the person racing after it on a train. Most people, when they first hear this, nod politely and think, sure, that sounds fine. But it's not fine. It's explosive. Because if light always travels at the same speed, regardless of how fast you're moving, then something else has to give, and the thing that gives is time itself. Let me show you why with something simple. Imagine a clock. Not a clock with gears and springs. A clock made of light. You take two mirrors, put one on the floor and one on the ceiling, and you bounce a pulse of light between them. Every time the light hits the bottom mirror, that's a tick. And simple, the distance between the mirrors is fixed. The speed of light is fixed. So the ticking rate is fixed. Good clock. Now put that clock on a train, a very fast train. From your perspective, standing on the platform, watching the train rush by, that pulse of light isn't just bouncing straight up and down anymore. The train is moving sideways, so the light has to travel a diagonal path to get from the bottom mirror to the top mirror and back. Think of it like this. If you're standing in a moving elevator and you toss a ball straight up, from your perspective, the ball goes up and comes back down to your hand. But someone watching from outside the elevator sees the ball trace an arc, a longer path, because the elevator carried it sideways while it was in the air. Same ball, same toss, but two different observers see two different distances traveled. With our light clock, the diagonal path is longer than the vertical path. But the speed of light hasn't changed, it's still the same. That's the whole point. Einstein's rule. Light always travels at the same speed, no matter who's watching. So if the light has to cover a longer distance at the same speed, it takes more time between ticks. The clock on the moving train ticks slower. Not because there's something wrong with it. Not because the mirror shifted or the light got tired. It ticks slower because that's what time does when you move. Moving clocks run slow. And before you say, well, that's just a weird property of light clocks, think about this. Every physical process is ultimately governed by the same laws. Chemical reactions, biological aging, the vibrations of a cesium atom, the beating of your heart. If time itself runs slower, everything slows down. You wouldn't feel it. Your thoughts would slow down at the same rate as the clock. From your own perspective, nothing has changed. But compared to someone who didn't take the trip, you aged less. That is not a metaphor, that is not poetry, that is a physical fact about the structure of the universe. Now, I can already feel some of you pushing back. You're thinking, fine, Feynman, that's a cute thought experiment with imaginary light clocks on imaginary trains. But real clocks, wristwatches, atomic clocks, surely those don't actually behave differently just because they're on a moving airplane. This is where we leave the land of theory and walk into the land of measurement. and the measurements are devastating for anyone clinging to the old idea. In October of 1971, a physicist named Joseph Hafele and an astronomer named Richard Keating took 4 cesium-beam atomic clocks, packed them into cases, bought airplane tickets for them, and flew them around the world on commercial jets. I want you to picture this. These weren't military flights. They weren't special NASA missions. Hafele and Keating walked onto Pan Am airplanes with regular passengers, families going on vacation, businessmen with briefcases, and sitting next to those passengers in the adjoining seat was an atomic clock. They actually bought tickets for the clocks. The manifest listed a passenger named Mr. Clock. The whole operation cost about $8,000, funded by the Office of Naval Research. It was one of the cheapest tests of a fundamental theory in the history of science. They flew east around the world first. Then they waited a week and flew west. When those clocks came back to the Naval Observatory in Washington, they were compared to the reference clocks that had stayed home the entire time. And the clocks disagreed. The eastbound clocks, which had been moving faster relative to the center of the Earth because they were going in the same direction the planet spins, had lost about 59 nanoseconds. The westbound clocks, moving against the Earth's rotation and therefore slower relative to the Earth's center, had gained about 273 nanoseconds. These numbers matched, within experimental error, exactly what Einstein's theory predicted. The prediction for the eastward trip was a loss of about 40 nanoseconds. The prediction for the westward trip was a gain of about 275 nanoseconds. The measurements landed right in the zone. Let me say that again, because I want it to sink in. They put clocks on regular airplanes, Pan Am if I recall, commercial flights with regular passengers. The clocks flew around the world, and when they came home they showed different times than the clocks that stayed put. The traveling clocks had literally experienced less time or more time depending on which direction they flew. That is time travel. A tiny amount, yes, billionths of a second. But it's real. It happened. It was measured. It was published. Nobody has ever refuted it. In fact, it's been repeated with better equipment, and the results only get sharper. But maybe you're still skeptical. Maybe you think there's some flaw in the clock, some vibration on the airplane, some temperature effect that explains the discrepancy. Fair enough, let's look at a completely different experiment, one that doesn't involve any human-made clock at all. Nature provides us with a clock. It's called a muon. A muon is a tiny particle like an electron, but heavier, and it's unstable. It lives for about 2.2 microseconds on average before it breaks apart into other particles. That's its lifetime. We've measured it very carefully in laboratories. 2.2 millionths of a second. Now, muons are created high in the atmosphere, about 15 kilometers up, when cosmic rays slam into air molecules. They come screaming down toward the Earth at about 99.9% the speed of light. Do the arithmetic. Even traveling that fast in 2.2 microseconds, a muon should only cover about 660 meters before it decays. 660 meters, the atmosphere is 15 kilometers thick. The muon shouldn't even come close to reaching the ground. And yet, we detect enormous numbers of muons at the surface. Every second, several muons are passing through your body right now. They're everywhere. The ground is being showered with them. How can a particle with a lifetime of 2.2 microseconds travel 15 kilometers? The answer is time dilation. From our perspective, standing on the ground, the muon's internal clock is running slow because it's moving so close to the speed of light. Its 2.2 microseconds of lifetime, as we measure it from the ground, gets stretched to something like 30 or 40 microseconds. That's enough time to cross the whole atmosphere. The muon isn't cheating. The muon isn't violating any law. Time itself is running differently for the muon than it is for us. And if you flip it around and ask the muon's perspective, the muon says, I only lived 2.2 microseconds, but the atmosphere was squashed down to a few hundred meters by length contraction. But the atmosphere was squashed down to a few hundred meters by length contraction. So I made it just fine. Both descriptions are correct. Both are consistent, and both require throwing away the idea that time is the same for everyone. So let me return to the thing I said at the beginning, the comfortable belief that time travel is fiction. What exactly have we shown? We've shown that two clocks that start synchronized can end up showing different times if one of them moves. The traveling clock literally ages less. If you flew around the world on those jets with Hafele and Keating, you'd come back a tiny fraction of a second younger than your twin who stayed in Washington. You traveled into that twin's future by the smallest amount imaginable, but you did it. You were a time traveler. And the only difference between you and the time travelers in the movies is a matter of degree, not of principle. This is where people usually stop me and say, all right, but these are nanoseconds, billionths of a second. Who cares? Well, the global positioning system cares. The satellites that tell your car where to turn are orbiting at tremendous speeds and sitting in weaker gravity than we experience on the surface. Both effects change how fast their clocks tick. If the engineers ignored Einstein's corrections, the position your receiver computes would drift by about 10 kilometers per day. The entire system would be useless within minutes. Every time a GPS satellite signal reaches a receiver, a relativistic time correction is applied. Time travel isn't just real, it's built into the infrastructure of modern navigation. But forget technology, forget applications. Think about what this means for the nature of reality. Time is not a river flowing at one speed. Time is more like a landscape with hills and valleys. Move faster, and you take a different path through that landscape. Sit next to something very massive, like a planet or a star, and time slows down for you compared to someone far away. Einstein's general theory of relativity adds gravity to the picture. Not only does motion affect the rate of clocks, but gravity does too. A clock on the ground floor of a building ticks slightly slower than a clock on the top floor. The difference is absurdly tiny, but it's there, it's been measured, it's real. Time runs slower when you're deeper in a gravitational field. Put it all together. Motion warps time, gravity warps time. The two effects sometimes fight each other and sometimes pile on top of each other. On the GPS satellites, the speed effect makes their clocks tick a little slower, about 7 microseconds per day. But the gravity effect, because the satellites are farther from Earth and in weaker gravity, makes their clocks tick faster, about 45 microseconds per day. The net result is that the satellite clocks gain roughly 38 microseconds per day compared to clocks on the ground. The engineers know this. They've programmed the correction right into the system. Every position fix your car's navigation system calculates depends on Einstein being right about time. Your head is aging faster than your feet right now because your head is farther from the center of the Earth. The difference over your whole life might amount to a few billionths of a second, but the principle is the same principle that would let someone in a very fast spaceship leave Earth, travel for what feels like a few years, and come back to find centuries have passed here. That's forward time travel. It's real. The physics permits it. The experiments confirm it. The only barrier is engineering. We don't have engines fast enough to make the effect dramatic on a human scale. But the effect is not zero even now. An astronaut who spent a year on the International Space Station came back having aged about 1/100th of a second less than the rest of us. Because the station moves at about 28,000 kilometers per hour. 1/100th of a second is not nothing. It's a measured fact about that person's biological age relative to everyone on the ground. What about backward time travel? That's a different story, and I want to be honest about it. The equations of general relativity do allow for solutions where a particle could travel along a path that loops back to its own past. These are called closed time-like curves. Some very clever people like Kurt Gödel showed that certain rotating universes permit them. But nobody has ever observed backward time travel. Nobody has a laboratory experiment for it. And there are very good reasons having to do with energy conditions and the stability of space-time to think it might be fundamentally impossible. So I won't lie to you, forward time travel is proven. Backward time travel remains an open question that most physicists are skeptical about. The universe seems to allow one direction of cheating but not the other. And I think there's something beautiful about that asymmetry, because it tells you that time is not what your intuition says it is. Your intuition says time is simple. Time is the ticking of a clock, and all clocks agree, and there's nothing more to say. Physics says, actually, time is woven into the fabric of space, and that fabric stretches and bends and warps depending on how you move through it and what massive objects are nearby. A clock is not just counting seconds. A clock is tracing a path through space-time, and different paths have different lengths. The elapsed time between two events depends on the route you take. That's the same as saying time travel is real, just stated with more precision. I want to leave you with an image. Think about the muons. Those little particles born 15 kilometers above your head, tearing through the atmosphere at nearly the speed of light. From the muon's point of view, it only lives a couple of microseconds. That's all the time it gets, a flash of existence. But from our point of view, it lives long enough to cross the whole sky and tap you on the shoulder. The muon is a time traveler. It lives in a different version of time than we do. And the reason we can detect it, the reason it reaches us at all, is because Einstein was right. Time bends, clocks disagree, and if you move fast enough, you can cheat death, at least from someone else's point of view. That is not science fiction. That is the world you live in, measured, confirmed, and operating inside the satellites above you every single day. What I want to know from you is this: if you could somehow ride alongside one of those muons screaming through the atmosphere at 99.9% the speed of light, and you only had 2 microseconds of your own time left to live, what would you think about? Tell me,